Hello, in this video we're going to look at ionic bonding. We're going to look at describing what ionic bonding is, firstly how you can tell which type of bonding is present. We're going to look at how we form ions, charges on different ions, and formula for ionic compounds. We're going to look at dot and cross diagrams, and we're going to look at the structure in ionic compounds and what properties that they have. Right, so one of the first things that students sometimes have a problem with is identifying which type of bonding is present in which particular compound. So when you're given a formula for any sort of compound, you've got the element symbols, and the first thing you should be looking at is which type of elements are present in that compound. So if we look at the first one, it's sodium chloride. Sodium is a metal, chlorine is a non-metal, ionic bonding. Hydrogen, non-metal, oxygen, non-metal, not ionic. Magnesium, and then we've got oxygen and hydrogen, so we've got a metal and two non-metals, ionic. So that's a very simple thing you should be looking at first when you get given a question on a compound and which type of bonding it is. So how are ions formed? We're going to take this in two parts. We're going to look at metal atoms and how they form ions, and then we're going to look at non-metal atoms and how they form ions. So the first one I'm going to use as my metal is lithium. And what I'm going to do is write down lithium's notation from the periodic table. So it's lithium 3, 7. So 3 is its atomic number, 7 is its mass number. And remember, atomic number tells me the number of protons, but that also means it tells me the number of electrons. So what I'm going to do is write lithium, and I'm going to draw its electronic configuration. So it's got 2 electrons in its first shell, and it has 1 in its second shell. So it's in group 1 because it has 1 electron in its outer shell. Now, atoms tend to lose or gain electrons to have a full outer shell. That makes them essentially more stable. So lithium only has 1 in its outer shell. So to get a full outer shell, it either loses 1 or will gain 7. And it will generally, metals, always lose rather than gain electrons. So because it's only got 1 in its outer shell, it's going to lose that 1 electron. And that now means it has a full outer shell. So it's lost its outer shell. The next shell in becomes the outer shell. So because it's lost an electron, electrons, remember, have a charge of -1. It still has the same number of protons. So if you lose an electron, you lose a negative, you become positively charged. So metal atoms always lose electrons to have a full outer shell, and therefore they have a positive charge, in this case +1. Right, non-metal atoms, and I'm going to use fluorine as my example. I'll give the notation up here. Fluorine is 9 and 19. So its atomic number is 9, that means it's got 9 electrons in total. So let's do the first shell. I'm going to do these as dots this time just to distinguish them between metals and non-metals. So that's 2 in the first shell, and therefore that leaves 7 for the outer shell. And that's why fluorine's in group 7. Right, fluorine could lose 7, but that's not going to happen. It's easier for it to gain 1 electron. So I'm going to draw the ion that's formed. So that's 2 in the first shell. You don't always have to draw all of the shells. And then it's got 7. Of its own, and it will gain 1. So non-metals gain electrons to form negatively charged ions. Because it's gained 1 electron, it will have a charge of -1. So you're always going to have positive metal ions and negative non-metal ions. So when you start looking at the periodic table, you should recognize that there are patterns for charges of different ions. So in groups 1, 2, and 3, we tend to have metals in groups 1, 2, and 3, and we have non-metals in groups 5, 6, and 7. So just to give you an example, I've got sodium in group 1. All of the elements in group 1 have 1 electron in their outer shell. And to form ions, they will lose that 1 electron. So sodium atoms become sodium ion. So anything in group 1 has a charge of +1. So sodium, potassium, rubidium, and so on. Right, so that's 1. 2, we've got magnesium. Could have picked anything in group 2. They have 2 electrons in their outer shell, and therefore they lose 2 electrons. So if you lose 2 electrons, that means you have a charge of +2. So all of the ions in group 2 will have a charge of +2. And then group 3, it's getting a little bit messy here. It's aluminium. It has 3 electrons in its outer shell, and therefore it loses all 3 to have a full outer shell. It will have a charge of +3. So you can tell what charge a metal ion will have in groups 1, 2, and 3, because group 1, always +1, group 2, always +2, group 3, always +3. So for the non-metals, in groups 5, 6, and 7, and I'm going to start with group 7 because it's the easiest one to look at, and we're going to pick fluorine, which I used in the previous slide. So fluorine has 7 electrons in its outer shell, and rather than losing 7, it gains 1 electron. Gain an electron, you now have a charge of -1 because you've got more electrons than protons. And then I'm going to go to group 6. I'm going to use oxygen as my example. Have 6 electrons in their outer shell, therefore they gain 2. Oxygen ions have a charge of 2-. And then lastly, 5, I'm going to use nitrogen as my example. Nitrogen has 5 electrons in its outer shell, and therefore it gains 3 electrons. So N 3-. So we've got F-, O2-, and N 3-. And that's just looking at the periodic table. That's how you can work out what charge different ions will have in different groups. So we have just looked at the charges of common ions in groups 1, 2, and 3, 5, 6, and 7. And they're quite straightforward because you can look at the number of electrons in the outer shell. This page is a little bit more confusing because we've got certain ions that you wouldn't necessarily be able to predict the charge on. Right, so hydrogen is one of those ones you need to learn. And that's got a charge of +1 because it loses its 1 electron that it has in its outer shell. So hydrogen generally forms +1 ions. Right, the rest of these ions are what we call compound ions. And that's because they're made up of more than one element. So you can see that hydroxide is oxygen and a hydrogen, but the charge of the whole ion is -1. The next ones get a little bit more confusing because they have multiples of different atoms. So ammonium is a nitrogen bonded to 4 hydrogens, but it has a single charge of +1. So don't get confused between the 4 and the charge. So the 4 is how many hydrogens it has, and the plus is the charge. The specification expects you to learn these different ions, and they can form ionic compounds. So you have to write formula containing these different ions. So it's worth learning these at this stage. Right, ionic compounds have a particular formula. And when we're working out what the formula is for an ionic compound, we have to make sure that the ionic compound overall has no charge. So that means the charges of positive ions and the charges of negative ions must cancel out to equal 0. And if we use our most probably well-known ionic compound, which is sodium chloride, the formula for that is simply NaCl. And why is it NaCl and not Na2Cl or NaCl2? That's because sodium in group 1 forms an ion of +1. Chlorine in group 7 forms the chloride ion, which has a charge of -1. And look at the charges, +1, -1, they will cancel each other out. So that's why it's NaCl and not NaCl2. I'll give you another example. MgCl2 is made up of magnesium ions, which are in group 2, so have a charge of +2, and they're made up of chloride ions, which are in group 7 and therefore have a charge of -1. If I was just to put one magnesium with one chloride ion, I would have an overall charge of +1 because I have too many positive charges. So that's why I need another chloride ion to get the 2 negative charges to balance the charge. So MgCl2. I'll give you a slightly more complicated one, which is ammonium chloride. Ammonium ions have a charge of +1. So we're going to do ammonium carbonate. Carbonate ions are CO3 but with a charge of 2-. Right, I've got 1 positive and 2 minus charges, so that's not going to equal 0. So what effectively I need is I need another whole ammonium ion to get the 2 positive charges. So 2 positives and now 2 negatives. How do I write that in a formula? Because I need 2 lots of that whole thing, I'm going to put the NH4 in brackets. CO3. Right, a really common source of exam questions is drawing dot and cross diagrams for ionic compounds. So that's where you draw the ions that make up the ionic compound. So if we start with a more straightforward one, we've got sodium chloride, which is NaCl. What you tend to get given the drawings of the atoms, and then underneath you have to draw the ions that make up sodium chloride, for instance. So if we go back, sodium has 11 electrons, so that's 2 in the first shell, 8 in the second shell, 1 in the outer shell. I'm going to draw the atom first. That's 2, 8, and 1. Hence why it's in group 1. And remember what we said when we formed ions, metals always lose electrons to have a full outer shell. So the ion becomes 2 and 8, loses that outer electron. So you don't need to draw the outer electron. And you put a bracket around it, has a charge of +1. Chlorine, non-metal, has 17 electrons. 2 in the first shell. Let's get a little bit messy. 2, 8. So that's 10, and then third shell has 7. Remember, non-metals gain electrons to have a full outer shell. So what you're going to be left with is chlorine. Let's draw the whole thing. Quite often you don't have to draw all the shells, but if they don't specify, please draw all of the shells. So it's 7, and it gains 1, and I like to draw this as a cross because you're showing that it's coming from the metal. If it gains 1 electron, it has a charge of -1, and you should be able to see that +1, -1 charges equal 0. Sometimes you're going to have to draw multiples where you need 1 metal and 2 non-metals, or the other way around, 2 non-metals and 1 metal. So you just need to make sure that the charges balance up, but make sure you've drawn the ion and you've drawn the charge, and that's how you get the marks in the paper. Right, we've talked lots about what ionic bonding is without actually defining what is meant by the term ionic bonding. So we know that metal atoms form metal ions, which are positively charged. We know that non-metals form negative ions, but those 2 ions are going to be attracted. Opposites attract. So the definition for ionic bonding, slightly long-winded, is the electrostatic attraction. So that's just the attraction between positive and negative charges. Electrostatic attraction between, and you could say positive metal ions and negative non-metal ions, but it's easier if you just write between oppositely charged ions, and that is the definition for ionic bonding. Anytime you're asked what is meant by ionic bonding, it's the electrostatic attraction between oppositely charged ions. So we've looked at how to draw dot and cross diagrams, and we've looked at charges on ions, but how do all these ions actually come together to form a compound, and what's the structure of the compound? Ionic compounds, you already know, if we looked at sodium chloride, for instance, it's the electrostatic attraction between oppositely charged ions, and that's what tends to happen. You've got 1 sodium ion and 1 chloride ion. In reality, those charges attract oppositely charged ions in all sorts of directions. Remember, these are little 3D objects very, very small. Every sodium ion is going to be attracted to all sorts of chloride ions around it, as many as can get around it. And this would be 3D. If I could rotate it, it would have another ion on the other side. And then that attracted to sodium ions, and then more chloride ions. You get this massive repeating effect. And this is called, and this is many, many thousands of ions that are attracted to each other, builds up to build this structure, which is called a giant ionic lattice. And helpfully, all ionic compounds have exactly the same structure. It's a giant ionic lattice. They might arrange themselves slightly differently, but it's this regular repeating arrangement of ions that we're interested in. So bonding is ionic, structure, giant ionic lattice. So the last thing we want to look at for ionic compounds is the properties that ionic compounds have. And if you think back to the most common ionic compound, or the one you're probably most familiar with, sodium chloride or table salt, it's solid at room temperature. And that gives you a clue as to its melting point. So ionic compounds in general have very high melting points. So you've got to be able to explain this. And it all comes back to the definition of ionic bonding. So you just need to add the word strong. But it's electrostatic forces of attraction between those oppositely charged ions and then the last thing, and you always write this when it comes to melting point, is a comment about how much energy it takes to overcome. So if it's got high melting point, because they're very strong electrostatic force of attraction, therefore they need large amounts of energy to overcome. And then we come to electrical conductivity. Does it conduct electricity? Now, electricity is the movement of charged particles. And if you think about ionic compounds, they're made up of ions. So if the ions can move, it can conduct electricity. If they can't move, it cannot conduct electricity. So in a solid, all those ions are packed together, attracted really, really strongly. The ions are not free to move. And therefore it doesn't conduct as a solid. But when can it conduct? When it's a liquid or in solution, so dissolved in water. And that means that the ions are free to move and carry the charge. And that's the two key ones. There are other properties, but these are the two that we tend to worry about the most. So melting points, always very high, and they do conduct, but only when they are liquid or dissolved in solution. So if you think about melting points, you're always going to find them as solids at room temperature. So questions will be, explain why sodium chloride, for instance, is a solid at room temperature. And you can use your explanation here. And then you might have questions about what do you have to do to an ionic compound to make it conduct. And that's pretty much it for ionic bonding.